will see in front of you these little sheets at the end of the session. I need you guys to fill it out. We use that for administration purposes. It's pretty much just like data that they collect, the university collects. I expect to use the full time. We'll probably end maybe like 5-10 minutes, just so that the other people that do the session after us, they can come in and get set up. So other than that, we're gonna get started. You guys can hear me all fine, right? Okay, cool. The way that I'm gonna structure this is not necessarily, I didn't make a final exam sheet or practice exam or any of that nature because I don't believe in those. What I did do, or what I will do, is that I'm gonna run through this textbook, which a lot of the students that came to my sessions prior to this, I used this textbook as basically a supplementary guide, and they did, most of them, majority of them, 90% of them did really well on their exam. And I did well on the ACS, I did well on my final, and I trust this textbook. It's the David Klein textbook. I'm gonna run through each chapter, give you guys a summary, give you guys golden facts, work 2 or 3 problems. We're just gonna keep moving. Sounds good? All right, let's get started. So chapter 1 is a general review of Gen Chem. Most of you guys probably forgot some of these things, but the moment that I give you a refresher, you'll understand. The biggest thing regarding organic chemistry with Gen Chem is hydrogen bonding and covalent bond and what's it called? Dipole moments. So when I look at something like this, something like this. Right? This is an ether, and I have an oxygen here. And essentially what this oxygen is doing, because it's electronegative, it's going to be pulling in these carbons into its electron radius. So you end up having a net dipole of going up. All right? That's pretty simple. We're not going to spend too much time on that. The next thing that I want to touch is boiling point. So something that has a lot of boiling point is going to be something that has lots of hydrogen bonding. Something that has a higher mass. So for example, something like, in comparison, you have something like this, 1, 2, 3, compared to something like that. This one will have the higher boiling point due to its mass. You guys see that? What else do we have? Also, you may see questions that it may not be as simple as this. You may have something like, let's say, something that looks like this maybe, versus something that looks like this, right? This one will have the higher boiling point. Oops, let me rewrite that. Due to it not having branches. So the more branches something has, it'll lessen its boiling point. Other than that, we're going to get right to chapter 2. So chapter 2 is based off of alkanes. I think most of you know how to draw an alkane, right? Your test may ask specific questions like, convert from line bond to the molecular formula, right? So you might go from like something like this, and they may ask you to go into the molecular formula. So this one would be CH3, CH2, CH2, CH3. Something that test takers love to do is they love to add something like this, right? COOH. What this is this is carboxylic acid. So a good way that they might test you is they may ask you, draw the molecular formula of something that looks like this. So basically what this is saying is that you have two carbons connected to each other, a methyl, and then another carbon, and then you have this carbon that's attached, double bond, to an oxygen attached to another oxygen attached to a hydrogen. If you count the carbons, 1, 2, 3, 1, 2, 3, you count the oxygens, 1, 2, hydrogens should all match up. These are easy points. The only way that you'd probably miss a question like this is if you miscount your carbons. I don't think your final will ask questions on line bond, or I'm sorry, not line bond, Lewis structure, so I'm going to skip over that. Another thing is functional groups. That's a big one that's tested. You guys should know all of your functional groups. I highly recommend, like, if you haven't, put them on flashcards and just go through them. Let's go ahead and do those. So you might have like an ester, right? This is a big one that people confuse with carboxylic acid, which is something that looks like this. This is a carboxylic acid. You might have something like an ether, alcohol, amides. Those are big ones that people often have trouble with. They might circle this, they might say amine, and then they might circle this and say ketone. That's not correct. So a good question that I picked up off the internet is something that looks something like this. So if I was to go through this, the first thing that I would do is I'd start at the top. I'd say that this is an alkene, right? Then I'd go through and say that this is a carboxylic acid. I'd say that this is a ketone. Some professors like to say that this is a carbonyl, which is correct. The reason why I say this is a ketone is that once all of you go through like Orgo 2 biochemistry, you'll start referencing this as a ketone. So this is also known as a carbonyl. So if you see a ketone on your test, know that's the same thing as a carbonyl. This is an ether. This is an amide. And this is an ester. This is not an alcohol. If I was to circle this and write that this is an alcohol, that would be incorrect because this is connected to this carbonyl, which creates a whole new compound known as carboxylic acid, right? The molecule itself changes its total identity, its properties, the moment that it's added to other functional groups. So this is just a sample. I think these are more or less the harder ones. I'm not going to go through all the functional groups because you guys should know them. And then we're going to go on to resonance. So resonance has 5 rules. And these 5 rules are They are, the first one is aromatic. So if you have an aromatic compound, it will always go and do resonance. An example of that is something that looks like this. So this is an aromatic compound, and what ends up happening is that all these alkenes kind of shift. So this is usually drawn something like this, or it may have this arrow going like this. It doesn't really matter. The point is that all these alkenes shift one, and they'll keep doing that and keep doing that. This is resonance. The most important thing to know about resonance is that it is not a different compound. Resonance just means that he's going from, you know, standing like this. He's going from standing like we're gonna say that this is the compound, right? This little stick figure guy. And he's gonna go from here to waving at us. Or that's a bad example. Where, yeah, he's gonna tuck in his leg. It's the same thing. He's not adding or anything like that. He's just changing the way he looks like. So it's the same thing. So if a problem on your exam has resonance, it's usually going to be shown in its final form on the multiple choice test. So let's say you do something and you're not understanding, like, why is my anti-choice looking like this? You probably miss resonance. It's something that's very commonly tested on because it's everywhere. Or go to biochem. So definitely know your resonance rules. The second resonance rule that we are going to do is an allylic lone pair. Okay. So an allylic lone pair is something that looks like this. Right? Double dot. This is also, that's the correct way to show it. You have your lone pair, and it's basically symbolizing that you have two free electrons. What's going to happen is this guy's going to go right here, and this guy's going to go like that. In essence, you have something that looks like this, okay? And they are shown in brackets. So, yep. So, brackets are important, as well as this double-headed arrow. If you see a problem on your test that does not have brackets, or it doesn't have a double-headed arrow, it just has one arrow, that's wrong. It must have the double-headed arrow, because that shows that it's undergoing resonance. If I don't show the double-headed arrow, it's saying that it's turning into a different molecule, which it's not. So let's do another one of these allylic lone pairs because people tend to have trouble with it. Let's go ahead and let's do this one. This is an oxygen. It has two lone pairs on it. This is a carbonyl. This is an ester, right? I would circle this and say ester, which is another way to integrate a problem, but we're not doing that. So allylic lone pair just means that this lone pair is going to go here, and this is going to shift up. In essence, it should look like that. Right. You have a positive charge on your oxygen because now you have 3 bonds on the oxygen, and you have a negative charge on the oxygen. Another thing about resonance is that the correct resonance structure or the final resonance structure will always have a balance of charges. If you don't have your charges balanced, you've done something wrong. If you started with a carbocation, or I'm sorry, a carboanion, you're going to end with a carboanion. If you started with a carbocation, you're probably going to end with a carbocation. So be on the lookout for that. So the next one, the third one, is called an allylic positive charge. So that basically has a carbocation that is allylic to an alkene. And this one is kind of like a windshield wiper effect. What ends up happening is that this guy comes and he just does that. Right, it's a windshield wiper effect. And remember what I said, if you start with a carbocation, you're going to end with a carbocation. Let's do one problem. So the first thing I do is I draw brackets because I'm going to show that this is resonance. I'm going to go right here, draw my double-headed arrow, redraw the compound. I'm going to draw this here. I'm going to move carbocation right there. It's just a windshield wiper effect. Okay. The fourth one is called difference in electronegativity. And then you can put in parentheses pi bond. Okay. And the way that that's shown is, let's say you have something like this. All right. What ends up happening in resonance is this alkene is going to shoot back up onto this oxygen. And as a result, you have something that looks like this. Negative, I'm sorry. Yeah, that's a negative, even though it connects with the G. Ignore that. And you have a positive here. Okay. And notice that your charges balance out. You started with a neutral, you end with a neutral. Alec lone pair, Alec positive charge. And the final one is lone pair that is directly adjacent to a positive charge. So the way that this is commonly shown is that you might have something, let's say, it looks like a neutral atom, and you have a carbocation right on top of there. Now what ends up happening is that because this atom has lone pairs within its octet, it will share it to try to alleviate the tension there. And as a result, you get something that looks like this. And now you have the positive charge on the oxygen. All right. I start with a carbocation, I end with a carbocation, right? So the biggest thing is that professors, well not professors, but test makers in general, they like to test the knowledge. So be wary of your charges, be wary of the double-headed arrows, and be wary of brackets. Because I guarantee you're going to have quite a few questions on your exam regarding resonance. Resonance is also integrated into other problems as well. So if you're doing synthesis and you get an answer and the multiple choice question does not show it, it may be due to resonance. But it looks like the same compound, but it looks a little bit different. See if you can do resonance and you may find the answer. So be wary. Okay. So now we're moving on to chapter 3, which is acid and base, which is another critical chapter that is often tested on the final exam very heavily. So acid and base is kind of a piggyback on what you guys learned in Gen Chem. However, there's certain rules regarding it. The biggest thing is there's this thing called Aereo. And this acronym is kind of a guideline on how you should approach acid-base problems. A stands for atom. R stands for resonance. I stands for inductive effects. O stands for orbital. What this acronym is used for is it tests the pKa value of a certain compound qualitatively rather than quantitatively. On your exam, you will not be given a sheet, even if like it's the ACS or whatnot. You're not going to get a sheet that says the pKa value of this is so-and-so, so-and-so, so-and-so. You know that a pKa, the lower the number is, the more acidic it is, right? And what Aereo does is it basically, you use this to compare the stability of your conjugate base. The more stable your conjugate base is, the more acidic that compound is. So let's do a couple of problems. So let's say we have a problem. I'm going to put this as A. We have a problem that looks like this. Right. And the test says, find the most acidic proton and explain why. The most acidic proton is determined by your conjugate base. The conjugate base of this is going to look something like this. Now I'm not going to draw the entire diagram on how to get to it because I don't want to take up too much time. So if this is your acid, your conjugate base is going to look like this. They're both going to hold a negative charge. What atom tells you is that the more electronegative an atom is, and how big an atom is, right? We go down a periodic table to figure out like how big an atom is. The lower we go, the bigger the atom is, and essentially, electronegativity goes up, right? It goes up and to the right. We know that oxygen is the more acidic compound, due to the fact that it fulfills the atom criteria regarding aereo. And that tells you that this is the more stable compound, therefore this right here is the more acidic compound, or the more acidic side. So if you add a base here, that base is going to come and steal a hydrogen from this side and not here, because this guy has the lower pKa value. Its conjugate base has the lower pKa value. So let's do one more problem. You guys see that? It's a thiol, and that's a hydroxyl. So the way that I would do it on a final exam, I draw it out. I say that this is my acid, and then I draw an arrow, and then I draw all my conjugate bases. Right. And I know that I'm comparing two atoms, so I go down the list of aereo, and I stop at aereo, or A, which is atom, because I don't see any resonance, I don't see any inductive effects, I don't see any orbital effects. So I look here, and I look at a difference in electronegativity, which there isn't because these both are in the same column. But I do know that sulfur is bigger than oxygen, therefore I'm going to circle sulfur and label that this is the more stable conjugate base, therefore this side is the most acidic. That hydrogen right there is the more acidic hydrogen. The next letter going down aereo is resonance. And resonance effect is basically something that looks like this. So when I go to show this conjugate base, I have something that looks like this. And you'll notice here that this guy does resonance, right? And resonance, this resonance rule is allylic lone pair. This guy's going to come here, and this is going to shoot to the top. As a result, you have something that kind of looks like this. I'll go ahead and put this in brackets. Right. So it does resonance. So I know that this side is the more acidic side, and that this hydrogen is the more acidic. Why? Because I went down aereo. I saw that both of these have the same atom, so I cannot compare through atom. Then I go down the list. I see R, resonance. I ask myself, do I see resonance? Well, yeah, this one can undergo resonance as long as I have its conjugate base, which I do. I do that, and I figure out that this is more stable than this guy. So therefore, this is the more acidic side. That is the more acidic hydrogen. We'll do one more problem. Where's that black dot coming from? I'm drawing in my hydrogen just for simplicity. You should know that there's a hydrogen there, right? Or two hydrogens, one hydrogen, another hydrogen, this hydrogen, another hydrogen. But I'm not going to draw the other hydrogen. So let's say I gave you a question, or the exam gave you a question and said, which of these two hydrogens is the more acidic? I know that from aereo, it can't be the atom, because once I put the negative charge on this carbon and I put the negative charge on this carbon, they both have the same atom. So I have to go down that list, and it's resonance. So I ask myself, well, do I have resonance? I go ahead and draw my conjugate base. I ask myself, do I see resonance? I say I do see resonance. It's an allylic lone pair. This guy's going to go here. This guy's going to go here. As a result, there's something that ends up looking like that. Right. So this hydrogen is the more acidic hydrogen, because that hydrogen undergoes resonance. So aereo is a flowchart that goes from here, and you just keep going down until you find something that makes sense. If you don't find something, you definitely did something wrong, and keep going down that list. The next letter is orbital, or I'm sorry, inductive effect. Some professors, when I was teaching this, had a different kind of acronym. Instead of resonance, they had orbitals come in front. If your professor has a different acronym, go by what their acronym is, right? So if they have orbital taking preference over inductive effect, go by what they say. Generally, this is kind of like the rule that applies. And a good way to check if you're doing it right is to check that compound. Look that compound up on like PubMed or something. And if that compound's pKa value is lesser than something else, then you know that it goes in that specific order. So yeah. So let's say I'm comparing two compounds that look something like this. I have acetic acid and a compound that looks like this. All right. And the test asked me which one of these compounds is more acidic. So I go down that list. I first draw the conjugate base. Conjugate base of this looks like this. The conjugate base of this. Looks like that. Okay. Now, if I go down that flow chart area, right, I notice that both of these have a negative charge on the oxygen, so it can't be A. Then I go down R. They both do resonance, right, because they're both doing allylic lone pair. This one can do this, and then it goes like that. Same here. So now I'm finally at I, right? I is an inductive effect. What that means is that you have very electronegative atoms that withdraw the electron density towards themselves. So you have a chlorine here, chlorine here, chlorine here. You may have fluorine, something very electronegative. And what it does is it's pulling the electron density towards itself, right? And that is what makes it a more stable conjugate base. So therefore, this compound would be the more stable conjugate base, and therefore this hydrogen right here would be the more acidic compared to this hydrogen right here. Okay, we'll do an example. Real quick. So this is very similar. And the thing about inductive effects is that it's an additive effect, so the more you have it, the more stronger it is. So if I was to compare these two and say which hydrogen, and I'm comparing these two hydrogens, is more acidic, I would say this one because it has inductive effects. Why? Because when I do aereo, both of these oxygens are going to hold a negative charge, so I can't do atom. Then it goes to resonance. Both of these do resonance. Finally, it falls on inductive, and I know that both of these have inductive effects. However, this one has more of an inductive effect due to the fact that it has one more chlorine. So the next one is orbitals. So if I gave a problem that was kind of like this, and I said, is this hydrogen acidic or is this hydrogen acidic? Which one is acidic? All right, that one or that one. I would go through the flow chart. Atom, both of them are on a carbon. Resonance, there's no resonance because the negative charge is going to be here and the negative charge is going to be here. Can't really do much. Inductive effect, no inductive effect, so I'm at orbital. sp2 is more stable than sp3, and sp is more stable than an alkene, right? So basically a triple bond is more than a sp3, right? Alkene is more stable than, or alkyne is more stable than an alkene. Alkene is more stable than an alkane. Okay. This one's pretty easy. I'm not going to really do another problem. I'm just going to keep going. Actually, another important thing is that if you are trying to predict the way that an equilibrium will shift towards the more conjugate base. Yeah. Towards the more stable conjugate base. What does this mean? This basically means that if I was to compare an atom or a reaction that looks something like this, and as a side note, all these questions are coming from the textbook, so they're like tried and through, so they're definitely right. Right. Which way will equilibrium shift? It's going to shift this way. Why? Because I compare my conjugate bases. This conjugate base, I immediately know that's aereo, and I can do that fast just just because I've seen this problem so many times. This electronegative charge is on this carbon, this electronegative charge is on the oxygen. So I'm at A for atom, and I stop there. This is a more conjugate base, therefore equilibrium will shift this way. This is something that I've seen a lot, so be wary of that and take good notes regarding equilibrium when you're studying. So now we're going to go on to alkanes. Let me just organize this. So in this chapter, it's pretty simple. So this chapter covers nomenclature as well as things like chair conformations and Newman projections, things like that. So I'm going to quickly go over that. You guys should know by now how to name, but just as a refresher, we're going to do something that looks like this. Common names will definitely show up on your exam, so I would study them. Your common names are things like isobutyl, secbutyl, tertbutyl. Some professors like to test like something like isopentyl. So if your professor has a favorite or something like that, pay attention to that. Know your nomenclature. Know that it goes longest parent chain, then it goes the shortest way through. So if you find a substitution on your number 1 as opposed to your number 8, you're going to go with number 1, and then you go alphabetically. It's pretty easy. So this one is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I know that my longest chain is going to be this way, so I'm going to write on the side, just for good bookkeeping, no name. And from here now we're going to start labeling our substitute. I know that there's a substitute there. I know that there's a substitute there. The shortest route through is 1, 2, 3, as opposed to 1, 2, 3, 4, 5, 6. Now I start naming. I know that I'm going to go this way. So 1, 2, 3, this is a methyl. 1, 2, 3, 4. This is a isopropyl. Isopropyl follows, ignore my spelling if that's not correct, but isopropyl follows the same rules. So if I was to name this, it would be 4 isopropyl, 3 methyl, nonane. All right. We want to be uniform. So if there was more than 4, or if there was more than 1 isopropyl, let's say it was here, it would be 4, 5 diisopropyl, 3 methyl nonane, etc., etc. The next thing that we're going to do is chair conformation. This is big, but before we do that, we're going to do Newman projections. So Newman projections is basically you looking down at a compound at a certain degree, and the question's going to ask, tell me what it looks like from this perspective. So they're not going to test you heavily on this, but I remember on my final there was 2 questions regarding this stuff. It's easy points if you know what you're doing. So by now we should know that wedges and dashes, wedges means that it's coming out towards me, dashes means that it's going into the page. So if I am, and this is my I, or sorry, I'm looking down at the page, or looking down at the molecule from here. Let's say this is the I, right? One I here, one I on the other side of the pen. I'm looking down, and I know that my bromine is going to come out looking like this. It's going to be out here, right? So when I draw my Newman projection, I know that this methyl is down, so it's down. So my peace sign is going to be inverted. And since bromine is coming out of the page, it's going to be on my top right. And there is a hydrogen on that side. It's going to look like that, right? Now on my back is always the invert of my front in terms of the peace sign. So this methyl is up, like that. And then I have a bromine that's going to go towards the bottom right. And I'm going to have a hydrogen that goes like that. I'm not going to spend too much time on that. It's a general idea. You need to know the general idea. And it's probably going to be something very simple. The next thing is conformations. For example, gauche, anti, and eclipse. You should know that eclipse has the most steric hindrance, therefore it has the highest energy. So in order of energy, eclipse has the highest energy, then gauche, then anti. So eclipse kind of looks like this. Let's say you had a Newman projection given, and you had something that looks like this. You have chlorine, and then in the back, you also have a chlorine all the way in the back, and it's eclipsed. So these two are eclipsing each other, therefore this has the highest energy. Molecules do not want to be in this formation because of reasons, so therefore in nature, when it's put in this conformation, it will immediately separate and it'll go towards its most stable, which is anti. So this is eclipse, and nature wants it to go. I'm gonna write nature. Nature wants it to go into a formation that looks something like this. Chlorine's here, chlorine's here. All right. These two are anti to each other. They're 180 to each other. Therefore, that is the most stable, and that's what nature wants. So gauche looks something like this. Let me redraw that circle. Let's say I have a methyl here and a methyl here. These two are gauche to each other because they're both the same molecule. So eclipse, gauche, and anti, they all have to do with the same molecule. If they're different molecules, it will still play an effect, but it won't play as big of an effect. So these two are gauche to each other, and nature doesn't want it. Nature will probably like orient this in an anti, or it might make this CH3 go like over here just to relieve the torsional effect, torsional strain, that's what they call it. No, this is Orgo. I'm not sure. You're going to have to go downstairs and ask. To Student Union. I go downstairs, all the way downstairs, and ask them. This is organic chemistry right now. Yeah. So the next thing is chair conformations. So this is another heavily tested topic that you can get easy points on. So chair conformations only deals with hexane. So let's say you have something that looks like this. This is a hexane molecule. You have something on a wedge and you have something on a dash. Wedges mean that the molecule, when you draw it in its plane, is up. Wedge means up. Dash means down. Okay? Wedge equals up. Dash equals down. The way to know, or to make sure that you are drawing your chair correctly in regards to equatorial or axial, is you draw a V, right? You come straight down, you come across, then you draw like a messed up Nike sign, and you just follow it through, right? You don't necessarily have to draw a different chair when you do the ring flip. You can just follow the same formula as long as you're consistent with your ups, downs, and things like that. I have a note here in regards to making sure, or how to stay fluid regarding your axial. So your axial will always be parallel lines in opposite directions. So if I was to draw all my axial lines, they're going to look like this. One line here, one line here. One line here, one line here, one line here, one line here. Those are all of my axial lines. Okay? Axial is always parallel and in opposite directions. Now my equatorial is always, they are pairs of parallel lines. So I'll go like that, like this, and like that, and like that, right? Together. Right. Your chair looks something like this. Right. So let's do something that looks like this. This bromine is on a wedge, so I know that it's going up. So when I go to convert this into chair conformation, it's going to look something like this. And when you go to number, right, it doesn't matter that you put your number 1 here, it doesn't matter. You can start 1 here, 2 here. The point is you need to be consistent. You need to transfer that numbering system over here. If I say that this is 2, but I start here, it's wrong because I'm no longer consistent. Just for simplicity, I'm going to go 1, right? So that's 1, right here is 1. Since this is up, my line theoretically needs to be up, right? That's its correct chair conformation. Now, you need to draw its chair flip. A chair flip, you draw a circle, or I'm sorry, not a circle, half circle with an arrowhead, and you always move 1 down. All right, so if I was here, then I'm going to move down, and I'm going to be up. This is up, right, in comparison to this, which is an axial position, but that's pointing down. You see that? This is up in comparison to this hydrogen, which is technically down, which is in its equatorial. The most stable conformation is when you have everything in your equatorial. So this is the most stable chair conformation. It's still up, it's just equatorial, right? We'll do one more problem. Let me pick something. So this one, this line is technically connecting, right? This is not an alkene, it's just connecting. So this is a methyl, this is an ethyl. Ethyl. ET and ME are abbreviations. So if you've never seen that before, ethyl just means, ET just means an ethyl. So if the test told you to draw the chair conformations and label the stable one, first thing you do is you draw your chair. You know that this guy's up. So I'm going to be 1, 2, 3. That's my numbering system. So 1, 2, 3, right? This one's up. This is ET. 1, 2, 3. This is down. So when I go to draw it, it's going to look like this. Right? It's at this carbon right here, and it's down. It's ET. When I draw its ring flip, I'm going to go one whole carbon down. So this ET or ethyl is going to end up right here. It's still in the up formation, so it's going to be here. And my methyl is also going to shift one, but still be in the down formation. So it's going to go from here to here. It's not going to be here because that is up. Rather, it's going to be here because that's now down. And when you try to figure the more stable conformation, you want your bigger guy on the equatorial. So methyl to ethyl, ethyl is more bigger. Therefore, this one is the more stable because ethyl is in its equatorial position. Okay, so a quick thing is cis and trans.
Is that supposed to be ME or is that on the third position of that chair conformation? Is that supposed to be ME or is that ET? Still two. Why is it 2E?
Oh, I'm sorry. Yeah. Yeah. Thank you. If you guys see mistakes like that, go ahead and just. This is ET and this is ME. Yep. Yeah. Please call me out on that. So cis and trans. So if something is trans to each other, it just means that. This is a bad example. These two are both cis, and they're syn-cis, right? Syn means same side, which means that they're both in the back, right? They're both on dashes, syn and cis, as opposed to something that looks like this. Right? This is now anti and trans. Right? That's something that will be like integrated. It's not something that's going to be directly tested on, because that's like, it's too easy of something that would be tested on. So we're going to move on to stereochemistry. So the big thing about stereochemistry is you need to know how to name things, right? Chirality. Something is chiral if it has 4 different flavors. What does flavors mean? Flavors, and I put that in parentheses, it just means that there's 4 different molecules, distinct molecules attached to that specific compound. So when you look at something like this, the carbon is here, it's got a Cl, an F for fluorine, you have an Et, which is ethyl, and you have an Me. This guy right here is chiral, right? But something that has two or more compounds that are the same flavors is not chiral. So this guy is chiral, not chiral, right? Four different compounds that are attached to each other. Through chirality, you know if you have something called an enantiomer, which is R to S, and you know that based off of assigning R and S, right? Based off of assigning chiral centers. On your exam, you may see something that goes from wedge to dash, even though that you know in like that's a simple shortcut that if something just changes from, let's say, wedge to a dash, it's an enantiomer. This is not the case for big compounds. You need to always make sure that you assign R or S, because when you don't do that, in a big compound, you may see that they all look like enantiomers, but when you go to assign configuration, you'll notice that one or more have the same configuration as the previous molecule. So, for example, it's not always the case, but sometimes it does pop up, especially like on exams like these, where they want to test your ability to name. Like, let's say you had a bunch of different, R means remaining, which means different things that are attached to it, and you had 4 different chirality centers attached to all these R. So this R was maybe like an S, S, R, S, and they all flipped, right? This guy maybe was like wedge, 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 and they all flipped into something that went all dash, right? So R. These all became dashes, and you think that, okay, they've all become dashes, so it's an enantiomer, right? That's not always the case. Let's say you went ahead and assigned, and you figured out that this guy is still S when it should have been R, right? So those things do happen, so please be on the lookout. If you don't remember how to do assign R or S, the way to do it is, it's called a rule of 3. So let's look at a compound like this. All right. This is not a chiral center, right, because it has 3 hydrogens that are the same that are attached. This is not a chiral center because I have 2 hydrogens attached, even though I have 2 different compounds right here. This guy is chiral because I have 1 compound here. Because if I have a wedge or a dash, I must have a wedge. My wedge is going to have the hydrogen, and I know that this guy is totally different from this guy, right, because this is an ether, and this is just an alkane, right? So the way that you do is you go ahead and number from 1 through 4. Number 1 is your biggest compound that is attached directly to that chiral center, and you do that based off a molecular formula. So, atomic number, based off atomic number. So this guy is number 1. because I immediately know that this is based off of atomic number, hydrogen is obviously number 4, right? Then this is going to be number 2, because this carbon is attached to that oxygen, while at the same time this carbon is attached to this chlorine, right? This is number 3. So what I do is I go ahead and see which formation, in terms of counterclockwise or counterclockwise, I can draw a half circle. So because it's 1, 2, 3, I ignore the 4 for now. 1, 2, 3, so it looks like this. But I know that my number 4 must always be on a dash. Even if my number 4 is not a hydrogen, it must always be flipped. So because this guy is on a wedge, I must flip it. So the correct way is it's going to look something like this. So instead of going like this, it's going to go like this, which means it's counterclockwise, which means that this specific guy is S and not R. Oh, I'm so sorry. Right? So again, 1, 2, 3, right? Go ahead and I follow. And I know that this way it's going clockwise, which means that it's supposed to be R, but my number 4 is on a wedge, so it has to be flipped because my number 4 must always be on a dash in order for me to keep the configuration the same. But since it's not, the correct answer is S. Sinister. Let me check time real quick. All right, so we're coming short on time, so I'm gonna try to figure out what's important from here, and we're gonna move. So let's say we had something that looked like this, right? These two guys right here are enantiomers, right? Now, if I had something, and it's an enantiomer because, I'm sorry, you need a reference. So this would be an enantiomer to something that looks like this. These two would be enantiomers to each other. But if I had something that looked like this, and it was in reference to something that looked like this, these would no longer be enantiomers. Rather, they would be meso compounds because there is a line of symmetry, right? I could cut these two in half because they're both literally the same parts. I can fold them over each other. These two are the same compounds. Even though they have chiral centers, they're the same compound, so therefore they're meso. So the way to figure out meso is symmetry. If you can find a plane of symmetry and something is on the same, both sides have a wedge and a dash, it's meso. You can get tricky with this, but I don't think you'd see something like that. You'd probably see something like that on a midterm for this specific chapter, but not on a final. A diastereomer is something that looks like this. Right? If a diastereomer of this would look like this. Right? They've all been inverted, however, this one is still the same. It's still a dash, therefore it's a diastereomer. So the next chapter deals with deals with Sn1 and Sn2. So I'm going to give you guys basically the quick facts regarding Sn1 and Sn2. We should all know that Sn2 and Sn1 have to do with substitution, right? The big thing regarding Sn2 is that you have a concerted process. So for example, if I was to draw this out, it would look something like this. I have a leaving group. That leaving group is going to drop. I'm going to have a nucleophile. That nucleophile is going to come, and it's going to do a backside attack, right? And as a result, you're going to have something that looks like this, right? You're going to have an inverted process. H, plus leaving group, right? This reaction loves primary, loves secondary, or loves primary, then secondary, but it will never react with the tertiary. It will always invert, right? And it loves strong nucleophiles. Sn1. Sn1 has something known as a carbocation intermediate, always. So you'll have a leaving group, loss of a leaving group. You'll have a carbocation intermediate. And you'll then have the nucleophile attack. And you will not have a backside attack because it does not need to do a backside attack. And you will have a racemic mixture. Racemic means you'll have 50-50 of whatever the chirality was. So if your starting compound was on a dash, you're going to have 50% dash and 50% on a wedge. This guy is the invert. He loves tertiary, then he does secondary, but he will never do primary. And it's always racemic. Also, these guys like apolar, or aprotic, I should say, aprotic solvents. These guys like protic solvents, right? A protic solvent is anything that has a hydrogen. So things like water, ethanol, those are common protic solvents. A strong nucleophile, aprotic commonly used is DMSO, right? There's not too much to know other than your nucleophiles. Some strong nucleophiles are things like anything that's a good leaving group, so iodine, Br negative, Cl negative. Weak nucleophiles, things like water and ethanol. You'll notice that the solvents and the nucleophiles are kind of the same thing. So Sn1 reactions do something called solvolysis, which is where the solvent acts as the nucleophile. So be wary of seeing racemic mixtures. I'm sorry, not racemic, but Sn1 not have a solvent. For example, you'll see something like this, just an arrow that does this, H2O, or just ethanol. Whereas something like Sn2 will have something like this. It'll have NaCl over DMSO, right? Don't worry too much about leaving groups because you'll get tripped up on leaving groups. But the more important thing is you need to see, in order to figure out if a reaction is going Sn2 or Sn1, always find the substrate, right? Go by this ranking system. Go by substrate. Go by substrate, then by nucleophile, then by solvent. Do not necessarily go by, what's it called, the leaving group. because oftentimes students get tripped up on it. So regarding these three factors, you can tell if something is going to go Sn1 or Sn2. I'll do one problem because we're actually running short on time. So a problem, for example, like this. So this is a secondary substrate. It's attached to two things. However, my nucleophile is something like this, right? I've never seen this solvent before, but it doesn't have a hydrogen attached, right? It's just HMPA, right? This, I know, is a strong nucleophile, and I know that this is a secondary substrate. So I can't go by the substrate, but I can go by the nucleophile and the solvent. Therefore, this guy's going to go secondary. It's going to do Sn2, so it's going to look something like this. In the end, it's going to look like that, right? So the next chapter is elimination. So elimination is kind of the same deal. The thing to know about elimination is sterically hindered bases like tert butoxide. Occasionally you may see DBU. It depends on like your professor if he likes to use DBU or not. These guys, they will always make your let me see. They will always give you a Hoffman product. What's a Hoffman product? A Hoffman product is always your least substituted, right? If I use tert butoxide, which is a strong base, but it's hindered, my product's going to look like that. However, if I was to use something like sodium ethoxide, right, NaOET, NaOET, with the same product, or same reagent, substrate, sorry. I'm going to get a Zaitsev. It's going to go there. It's going to be the more substituted alkene. So keep that in mind. The way to really hammer this in is to really do a lot of problems. And you always know that when you do something like this guy is going to be your major product, and you're going to have 99% of this in your solution, and you'll probably have like 1% of 1% of your Hoffman product. But this will be 99%. And this will be like 1%, your Zaitsev product, right? So your least substituted is always called a Hoffman product. Most substituted is your Zaitsev, right? So another important thing is that regarding textbook here. No, I can't even show it. But there's these things called strong nucleophiles and strong bases. What these can do is that these guys can act both as a nucleophile and a base. And common examples of these are things like NaOT, which is or NaOMe. These two are the most commonly used. Right? These guys can act both as a nucleophile and a base. So if you have a primary substrate, right? And the question asked what is the product, and the reagent was NaOMe, and you knew that your substrate was primary, it will go nucleophilic. It will do a nucleophile substitution. It will go Sn2, right? Not Sn1 or E2. It's going to go Sn2 is going to be your major. If I give you a secondary substrate with sodium methoxide, it's going to go E2 as your major product, right? Your Zaitsev will be your major product. And your tertiary, if I give you a tertiary with sodium methoxide, you're only going to get E2, right? So that's something that you should know regarding strong nucleophiles and strong bases. So the next chapter is addition of alkenes, right? This one is kind of straightforward. This one is basically knowing your reagents. So you might have things like Br2, like an alkene is being reacted with Br2, right? The only way to know this is from pure memorization, and you know that this is going to go like this. Right? It's going to be anti. Or if I add something like H2PT, it's going to clear out the alkene and just add hydrogens there. I wish I could go through all of them, but I necessarily can't because of time. But the only way to know these for your exam is just pure memorization. These are heavily tested, like you're going to probably get like 2-3 problems on it. So you need to know, like, for example, this is anti-conformation. One is on a wedge, one is on a dash. To get Sn conformation, you would use something like to get Sn conformation on any of your alkenes, I think the only reagent is OSO4. With this solvent, which I don't know. And essentially what this will do is it will add Sn oxygen. I believe that's the only addition reagent that adds Sn. Almost all of them add anti. So for these, I just recommend you to memorize them. Put them on flashcards and just go through each and every single one of them. Alkynes are the same way. So alkynes have, like, there's two that I'm going to go specifically over. that you need to pay very good attention to. So if you have an alkyne and you are given you are given a solvent that looks like this, CH3 or CH32. It could be anything, but it has BH at the end, and it's undergoing with this compound. You know that you will get a you will get your ketone to be terminal. It'll be at the end, right? And this is basically an anhydride, right? Oh. I'm sorry, an aldehyde. You'll get an aldehyde, right? If you use a compound that follows this formula right here. This guy will make a anhydride. If I use sulfuric acid, with mercury sulfate, I get a ketone, right? The carbonyl will not be terminal, it'll be on the inside. So these two, be wary of, because students often get them tripped up, so be careful. Another thing that you should know is regarding how to add to an alkyne. Right, you used the following reagent. You use 1 sodium sodium ammonia with a halogen attached to whatever you want to add. So if you want to add an ethyl, you would do this. If you wanted to add a propyl, you would do something like that, right? But that's the general formula of how it goes. Be wary of hydrogen. So Lindlar's Catalyst will turn an alkyne into a cis alkene. Sodium ammonia, which is known as a poison catalyst. I'm sorry, not a poison catalyst, a dissolving metal reduction. Turns it into a trans alkene. So what do these look like? So the Lindlar's Catalyst basically looks like this. You'll have an arrow, H2, Lindlar's. This one. And a dissolving metal reduction will look like this. So if I had something that looked like this, and I did Lindlar's Catalyst, right? I'm going to have something that ends up looking like this. Cis, right? And if I go sodium ammonia, I get something that looks like this. A trans. So after this, alcohols and epoxides. So we're going to start with epoxides. So an epoxide basically generally looks like that, right? The thing that you should know is that if you are reacting an epoxide, let's say we're gonna make that our epoxide, and I react this with any strong nucleophile of my choosing, let's say NaSH with water, you will have an Sn2 reaction. Basically what that means is the mechanism kind of looks something like this. This guy's going to come to your least substituted side. It's going to attack that carbon. This carbon is going to come on top of the oxygen, and it's going to fling in this direction, right? It's kind of like a slingshot. It just flings in the direction that opposite of the attacker. So the attacker is attacking this way, it's going to attack that way. Or it's going to fling that way. So it ends up looking like this. SH is going to be here. And this is going to fling that way. Then the second thing that's going to happen is this water molecule is going to come. This negative charge is going to come pick up this hydrogen, break this bond, and I'm going to follow this over here. And it's a three-step mechanism. 1, 2, 3. All right. So that's what your product's going to look like. If I come back here, my product's going to look like this. And this is for any strong nucleophile. So the general formula is that for a strong nucleophile and an epoxide, it's going to attack in an Sn2 formation. What that means is that it will attack the least substituted it will fling open. And water will protonate. And this is for any strong nucleophile, so it doesn't matter. Like here I used this, right? I could have put NaOH, I could have put NaCl, I could have put NaCN. It's just any strong nucleophile. So that's really big on epoxides. You'll probably see like 1 or 2 questions on that. Regarding alcohols. So you need to know what a reducing agent is, and you need to know what an oxidizing agent is. So a reducing agent get to that chapter. Is anything like these three. Sodium borohydride with methanol. H2PT, right? Or LAH with water. So essentially what these do is they will take something like a ketone, and if I add LAH, I get something that looks like this. Right? It has reduced this ketone into an alcohol. You should know that LAH is specifically stronger than all of these three. So what LAH does is that if you have something like an ester, right, and I react it with LAH, what it will do is it will break this bond right here, and a result what you get is, whoops, sorry. You get something like this. You get an R. There's an R here. R here. You get something that looks like this. And when it breaks this, this gets cleaved off, and essentially what you get is you get a methanol right here. So the way that I used to always do it was that I would just add an H to wherever it was. So if this is OET, I would have ethanol, right? If it was OPR, propanol. So LAH is definitely, it's something that is stronger than the rest of them. So I would know the properties regarding LAH, H2PT, and sodium borohydride, when you can't use it. Another thing is that when it's used with an ester, I forgot to note that this is an excess, right? So anytime it's used with a ester or a carboxylic acid, it's an excess. So if it's used with a carboxylic acid, I forgot to write H2O here. Nothing's going to get cleaved here. It does get cleaved, actually. But what I meant to say is that you're not going to have something like MEOH. Rather, you're just going to have water. Because when this gets cleaved, a hydrogen gets added to it. But you do not necessarily write the water. You just leave it out. And it ends up looking like that. You need to know what your oxidizing agents are. So a very common oxidizing agent, which is like tested on all the time, is PCC. So if you have something that looks like this, and I add this to PCC and CH2Cl2, this is going to create a anhydride, right? It's going to look like this. These are oxidizing. Another commonly used oxidizer is sodium chromate. The thing that you should know about sodium chromate is that if you use it with a primary alcohol, like this, and I use sodium chromate, and I use that with sulfuric acid, I get a carboxylic acid. If I use it with a secondary alcohol, I get a ketone. Or carbonyl, right? So know the properties regarding your oxidizing and your reducing agents. Know what sodium chromate can do and what PCC can do. PCC cannot do these. Only sodium chromate can. Okay, so the final stuff we're going to cover is Nmr, Ir, and Mmr. So there's not a whole lot that I can show you regarding that. I know that many of you took your test already, so it should be fresh in your mind. The big thing to know about IR is to know your numbers. Memorize your numbers. Memorize what certain patterns look like. For example, carboxylic acid is something that has a very strong pattern, right? Can't necessarily draw it out, but you know that there's a sharp peak. So this is for IR. So for carboxylic acid, you know there's a sharp peak at 1700, around 1700, and then you know that at around like 2500 to like 3500, you have a very broad peak. So I'm going to try my best to draw something like this. So it would look something like this. Very broad, sharp peak, right? And this is like at 1700, and this is at like 2500, and this is like 3500. Right? So no distinct patterns. Your professors will usually tell you which functional groups that you should know. So big ones are things like alcohol. Alcohols are usually around 3200 to 3600. Know that when alcohols participate in an IR spectrum, if they are undergoing like hydrogen bonding, then they're broad. So alcohols that are in hydrogen bonding, they will be around this area, but they will be broad, right? If they're not, then they're sharp. Know that for amines, if you have a primary amine, you're going to have two peaks. If you're having a secondary amine, two peaks at around 3500. Secondary amine is one peak at around like 3500 as well. So know these distinct patterns. These are commonly tested because IR is something that's like, it's usually, traditionally it's taught in Orgo 2, but this semester they kind of like push it into Orgo 1. So I don't necessarily think, especially since you guys took an exam, that it would be tested heavily on. But regardless, you guys should still know. So I have about 4 minutes, so I'm going to rush through the rest. So what you should know about MMR is that MMR and IR are used in conjunction with each other. IR tells you the functional group, MMR tells you the molecular weight of the compound, pretty much. So your M plus is not, this is a common misconception, it is not the molecular weight, or it's not the base peak. It's not your tallest peak, right? So your tallest peak, just because if you have a bunch of lines and this is MMR, and let's say these are your lines. Some students tend to think that this is your M plus. This is not your M plus unless it's specifically stated, right? This might be your M plus, this might be your M plus. Another thing that students tend to like not know is that if you figure out that, if you were to say that this was your M plus, right? This was your M plus peak. This would be your M plus 1. This would be your M plus 2. This would be your M plus 3, M plus 4, etc., etc., etc. There's two patterns that you guys should know regarding chlorine and bromine. So if your molecular ion, if you figure out that your molecular ion for example, you figure out that this is your M plus peak, right? This is your M plus. For bromine, if your M plus 2 peak is the same height as your M plus peak, then it's bromine, right? Bromine equals same height as base peak, M plus 2. So this is M plus 1, M plus 2. Chlorine tends to be 1/3 of the height. So 1/3 of this would look like that. So chlorine equals same height, or sorry, 1/3 of the height of M plus, right? So M plus 1, M plus 2, that's 1/3 of this height. So I know that when I do my MMR, I have a chlorine. The thing to know about NMR, which deals with hydrogens, is that NMR likes to basically look at a specific compound, and it kind of, what it does is it analyzes all your hydrogens, all the groups of hydrogens that you have. So this compound has a bunch of hydrogens, right? However, you have some of the same hydrogens, right? This guy has hydrogens attached to its methyl group. This guy has hydrogens. This guy has hydrogens. This guy has hydrogens. This guy has hydrogens, etc., etc., etc. Your NMR graph will not show all of them. Rather, it will show specific groups. And the way that these groups are found is basically by how distinct those hydrogens are. And the way that they're distinct is if you find symmetry between these hydrogens, then they are categorized into one group. For example, these hydrogens right here, they're both the same. So these guys are one whole group. These hydrogens marked by symmetry are also the same, right? Because they're both on opposite sides. So these guys are both the same. So now you have two groups of two distinct things will show up on your graph. You have a hydrogen here. This guy's distinct, so that's a third. You have hydrogens right here and right here. These two are the same, so you only have 4 now. You also have, attached to this methyl, you have hydrogens. But because I don't have a methyl, a methoxide on this side, the hydrogens that are attached to this methyl group right here are distinct. So you are going to have a 5 total. You will have 5 total signals. Yep. And the last the last thing that you should know regarding NMR is something called N+1. So N+1 tells you if you have a singlet, doublet, triplet, or what have you. The way to figure this out is that if you have a compound that looks something like this. Right, and the question asks, these are CH3s, and it asks how many neighbors do these guys have? Well, I know that all these hydrogens will be one signal because they're all the same. They're on a methyl and they're all like they're their own group. So these guys right here will have one carbon, or I'm sorry, one neighbor, because directly attached to this carbon, to its intermediate, has a hydrogen. So it has one neighbor. So N+1. N is the number of neighbors you have. Since I only have one neighbor, this guy right here is going to be a singlet. Oh, right. I'm comparing the carbon right here, these carbons right here. I'm sorry. I'm not comparing these carbons. So if I was to compare this carbon, I go directly to its adjacent, this guy right here. Since this guy does not have any hydrogens, it's 0. So 0 + 1, singlet. If I was comparing, let's see, this guy right here. This guy right here would have 2 neighbors because right here I have 2 hydrogens, right, directly attached. I don't have any neighbors here, I have 2 hydrogens here. So this guy right here, N+1, 2. So this would be a triplet. Okay, so with that, I'm pretty much going to end the session because other people have to come in for their next. So if you guys could please just fill out those evals and clean up after yourself, I'd be greatly appreciated. Other than that, thank you for coming, guys.